So I want to actually have us think more about these systems of linear equations with lots of variables and lots of equations. You know, there are different types of possibilities that we've seen that could happen when we're looking at solving a system. There could be one solution, there could be infinitely many solutions, and there could be, in fact, no solutions. And I just want to offer a couple of little words about each one of those things. Let's have a look. So if, in fact, we have exactly one solution, then we actually call that system consistent, or sometimes independent. If there are infinitely many solutions, then we call the system consistent and dependent. And if there are no solutions, then we call it inconsistent. So basically, if there are any solutions at all, we call it a consistent system because it means there's some solution. There might be only one, or there could be infinitely many. And if there are no solutions, then we say it's inconsistent. If there's exactly one, then we call it an independent. And if there's infinitely many, then it's actually called dependent. So these are just more of a vocabulary list of anything else, but if you see these words, I want you to know what they mean. And more importantly, I want you to understand kind of what they represent. So let's just take a look at some examples. Two equations, two unknowns. So here's a couple of systems. So y equals negative x plus 4 and y equals negative x plus 1. Here's a different system. Y equals negative x plus 4 and 2y equals negative 2x plus 8. And then finally, a third system, which is y equals negative x plus 4 and y equals 2x plus 1. And what I want to do is I'm going to show you various graphic images of one of these collections, and we have to figure out which one corresponds to which system. So there are three candidates here. It's kind of like a match game, if you will. It's the linear system match game with your host, Ed Berger. Thank you. Thank you very much, ladies and gentlemen. Thank you. Now, there is so much excitement to the game that I can't even show you all of them at once. But I'm going to do my best to see if I could sneak them in here. I've got to have a conversation with my art team. Tell them exactly what I need. So here are three different pictures that correspond to three different systems. And now our job is to match the system with the actual equation. So let's take a look at some examples. So let's take a look, for example, at this one. So y equals negative x plus 4 and y equals 2x plus 1. Let me tell you how I think about these things. These are two equations in x and y and two variables, so they represent lines. That's good. All these things are lines. If anyone was a curve, I could throw them away immediately. And so we can look at the slope, right? So the slope of this line is negative 1. The slope of this line is 2. So those are different slopes. So I should be looking for a system, an image, where we see two different types of slopes. Well, these are parallel lines, so they're actually going to have the same slope. Here's only one line I see. But here I see a graph with two lines having different slopes. In fact, one is negative, that must correspond to this negative one, and one is positive, that must correspond to that one. So in fact, I say that this system corresponds with this. This, since there's exactly one solution, that's where they meet, the two lines meet up. There's one solution, so it's consistent and it's independent. Awesome. Ding, ding, ding. That's a winner. Now we've got two candidates left for the two graphs. So let's take a look. Which one should we look at next? How about if we look at this one? Here I see again two lines, and I see that their slopes actually now are the same. Negative 1, negative 1. So that tells me, in fact, that these two people are going to have slopes that are the same, parallel lines, and these tell me the y-intercepts, so there's different y-intercepts. So I'm looking for two lines that are parallel that have different y-intercepts. Which of these two? Well, it's this one, of course. In fact, this one you can see has a y-intercept of 1, that corresponds to this. This has a y-intercept of 4, so that corresponds to this. So in fact, this is a match. And what do we see here? Here we see no solutions, because parallel lines never intersect. So this is an example of an inconsistent system, so that's kind of fun. And then finally, this must be here by process of elimination, but let's actually also just think about it and make sure that we really, really believe that. How can I see that? Well, one thing I can do is say, this is sneaky. Why is someone putting a 2 in front of the y? We don't do that normally. Let me divide everything through by 2. The moment you divide everything through by 2, what do you see? You see y equals negative x plus 2 divided by 8 divided by 2 is 4. So I see negative x plus 4. And that's exactly the same thing as the first one. So these are just two equations that have been duplicated, right? It's the same exact equation, in fact. And that's why the graph is a little misleading. There are actually two lines here, but we can't see them because they're literally right on top of each other. They're right on top of each other, which means that what do they intersect? Absolutely. In fact, they intersect at every single point, infinitely many solutions. Therefore, this is consistent but dependent, because the second equation actually depends on the first one. So there you can see three great examples, so thank you all for playing. In fact, I'm going to keep two of the candidates here just for fun. And let's actually verify for ourselves what we observed visually through a little bit of algebra. So if we take this system and now try to solve it using elimination, what do we see? Well, let's eliminate the variable y. To eliminate the variable y, since y equals this, I can plug that in for the y here. So substituting this into here, I see negative x plus 4 equals negative x plus 1. And now you kind of want to get all the x's to one side, right? So I guess what I'll do is I'll just add x to this side to get rid of it and put it on that side. So if I add x here and add x here, what do I see? Well, they cancel here, but notice they also cancel here. This is kind of unusual. You don't usually see this in our equation lives. But they cancel here. The x's just go away, and I'm left with 4 equals 1. Well, 4, it turns out, I've looked this up in the math handbook, it doesn't equal 1. So this actually is a false statement. And what does it mean to have a false statement? It means that these two equations can't be satisfied simultaneously, which means there are no solutions, which means this is an inconsistent system. And we're verifying that for ourselves, because if you assume both these are true and use elimination, you get something that's absurd. So therefore, they both can't be true. Now, easy enough. OK, great. So now we verified that algebraically. Let's take a look at this system. Remember, this we saw had infinitely many solutions. Let's verify this for ourselves using substitution. So if we use substitution here, what do I want to do? Well, what I want to do is I'll actually multiply the top equation, let's say, by 2. So multiply the top equation by 2, then I see 2y equals negative 2x plus 8. And then I copy down that second one. And now what I'll do is, to try to get rid of the y terms, I'll just subtract both sides from each other. So that 2y minus 2y will actually add to give 0. So that's kind of awesome. But notice on the right, there's a lot of awesomeness. Negative 2x minus negative 2x, that's 0. And 8 minus 8 is 0. And so here I see 0 equals 0. Now, that's something that's always true. And notice that that has nothing to do with x or y or anything. That's just a fact, which basically tells us that there are going to be infinitely many solutions. There'll be infinitely many solutions. And in fact, if you give me any particular x, I can find a corresponding y that will satisfy both of them. So here again, we can see the algebraic manifestation of what we observed visually looking at the graphs. It's really cool to see that linear systems can have lots of different possibilities. One solution, infinitely many solutions, or no solutions. And our job is to figure out how many there are, if any at all. I'll see you soon.